course, we're guilty when we're participating in challenges on this, but at the same time, you know, it helps us to maybe find a good surrogate for the kind of problem that we actually want to solve in the end. In our case, I think it would be really, you give the images as input and you have your map features as output, and how do we, you know, measure the accuracy of those map features? And something that we came across, because we had to take all these intermediate and twisted paths in between, is you know, look at the metric that produced or rated the results that we got, for example, on Kitty 3D. And that's what my last part of the talk will be all about. Kitty 3D, this is how, from the competing methods that you've seen before on the leaderboard, on this comparison of results, that's how a PR curve, so a precision recall curve, very often looks like. So we all agree it should be somewhere here and there. The reality looks like this. Okay, let me try to break this down. What Kitty is actually doing, it computes the average precision given a set of, let's say, bins on the recall level. So you have an interval that tries to approximate the curve under the precision, so the area under the precision recall curve. And the formula here on the top left, this is something that was somehow shown in the 80s, and it was used in the Pascal VOC challenge in 2007 to 2010. And it's something that people built on top of it. And there's hundreds of papers that evaluate it on top of using this metric. And today I'm claiming that this metric has a flaw, a serious flaw. And this flaw is actually appearing very dramatically when we look at monocular 3D object detection, because we're not operating at this spectrum, but we're operating somewhere here. And the critical part can actually be seen here at this part. So when the precision recall curve is generated, the metric here eventually just sums over this kind of intervals that are defined here, and this is this R11 spacing. So it just takes 11 equally spaced points on the precision recall curve. And maybe you see where I'm going here. When you do this, there's this strange peak here at the beginning. And if you look at the leaderboard, the publicly available leaderboard of the test server of Kitty 3D, you see that spike very, very often. I would like someone in the room to explain me what it actually means to have 100% precision at the recall of 0. So I really don't know. But what we found is, assume you have tens of thousands of cars that you predict, right, on the Kitty test set. And now assume that you throw away all of them except for the best. And with the best, I mean the one where you have the highest confidence on your predictor. Whatever you use for confidence, I don't care. You reduce the entire data set on the test server or also on the validation to a single hypothesis. And now comes the catch. If you submit that to the test server, it will tell you that you're performing at about 9.09%. And that's like 4 or 5 times better than the state of the art that's currently on Kitty 3D. And we feel like that's not the right metric to assess where we are at 3D object detection. Yeah. So obviously, we try to first debug our code and have a look, and did we do something wrong on our side? And of course, we made many mistakes, but that wasn't one of them. So we're really happy to hopefully contribute this back to the community. We hope that people from the Kitty server pick this up, and there's actually, this flaw is not present in the nuisance challenge. They have a different score and different metrics that they use. But this is something that needs to be fixed. And the problem is, if you fix this, the scores get even lower. So there's a lot of work left on the 3D object detection side, but this is a really exciting topic that my team and I are working currently. And this is basically the single correct hypothesis per difficulty level that reaches the score. And you see that actually all of them except of this one is lower. And these are all works that are state-of-the-art on 3D object detection. So the metric is poor. We need a proper metric to assess what we're actually doing. Okay, we also identified